Hi, today I'm going to discuss the solution for Atcoder Beginner Contest for 30 problems A to F. And let's first start with problem A. So for problem A, there's a law that a person who possesses A or more candies must possess B or more cookies. So Takahashi possesses C candies and D cookies, and we need to determine whether Takahashi is violating this law. For this problem, we can directly check whether C is greater than or equal to A, and if so, if D is less than B, then this is violating the law, or otherwise it's not. And we can check this using a if statement, and let's directly look at the code. So here is my code for problem A. I first inputted the values A, B, C, D. Then I checked if C is greater than A. So this is the first part of the law, which is if a person has greater than or equal to A cookies, they must have at least, candies. If greater than or equal to A candies, then they must have at least B cookies. So if they have greater than or equal to A cookies, and if they don't have at least B cookies, then this means that they're violating the law, and we output yes. And once we have an answer, we can return 0. And otherwise, if we haven't stopped the program, then this means that they haven't violated the law, and we will output no. Next, let's look at problem B. For problem B, we have a grid with n rows and n columns. The cell at the ith row from the top and jth row from the column both is either painted black or white. So it's this symbol if it's black and a dot symbol if it's white. So we need to determine how the number of distinct patterns of painted cells that can be obtained by extracting a region of m rows and m columns from this grid. So since the grid is small, we can directly use a set to check all the possible patterns that we obtain. So we can use a set of vectors of strings. So a vector of strings would contain this region of m rows and m columns. So we would have a vector that contains m items, and each item is a string of length m, representing a specific row. So some m characters would be in a string, and these strings will all be stored in a set, in a vector, and the vector would then be stored in a set, because we can use a set because a set automatically removes all duplicated items. So if we add these vectors into a set, then in the end, we can just check the size of the set to obtain the answer that we want, which is the number of distinct patterns. And now let's look at the code. So this is my code for problem B, and I first defined my grid. Then this is the set of vectors or strings that I just mentioned. And I first inputted all the values. Then I looped through. I and J is the starting point of the m rows and m columns. So I loop through all possible top left corners that I can start with. Then I loop through my region, which contains m rows and m columns. So here is, I start with I and j, and then for each I loop through m. So m characters each, and this forms a region of m rows and m columns. And then for each row, I store it into a string. So I add the characters into a string called s1. So here, s1, I define s1 here, so it like redefines each time as an empty string. And then I add the m characters of each row into that string. Then I push it into my vector, which I define here, called v. And this vector would store m strings in the end, each string representing the characters of each row. So after I pushed all these strings into my vector, I will then insert this vector into the answer set. And the set would automatically ensure that my my results are all different from each other. So this would give my answer. The size of the set would be the answer that I'm looking for because the problem is asking for the number of distinct patterns. Let's look at problem C. So for problem C, um, we have a rule in Atcoder country that a truck driver must take a break of at least B minutes when driving for A minutes or more. So what we want is that we have a string of length n that consists of characters A and B, and also we have positive integers big A and big B. So we want to find integer pairs L and R that satisfy the following conditions, that L are inclusive, and in this region, the number of A's is at least big A, and the number of B's is less than big B. So let's see how we can solve this problem. We can use prefix sum to solve this problem because um, we can't just loop through all possible values of L and R since um, n is equal to 3 times 10 to the power of 5. So if we loop through all possible values of L and R, then that would give a n squared solution, which would exceed the time limit. So we need to find a quicker solution. And we notice that the condition is just to find the range where the substring has characters A greater than or equal to the number A. So we need to have at least a number of the character A in our substring. And we can't have more than B number of the character B in our substring. So what this means is that we need the number of A's and B's respectively in our string, and we want to calculate this quickly. So if we want to do this, we can use prefix sum because this would directly give us like the number of A's and B's in a certain range without having to calculate it each time. So using prefix sum will allow us to calculate the range, like the number of A's and B's in a particular range quickly. So after we do this, we can then loop through the number L. So we want to find like possible L's and R's, right? And so if we loop through each L, then we can find the minimum and the maximum possible R values that would work. So there would be a range of R values that would work, and if we subtract the minimum and maximum, then we can find the possible number of R values that will work, which would give us the number of R values for each L. And if we sum them all up, then we can get our answer. And so next, we're aiming to find the minimum and maximum possible values of R. And to do this, we can use binary search because we only have two conditions. One, which is that the number of A's in the string is greater than or equal to A. So this would be the minimum value. So the minimum value is that A's, and the maximum value will be the number of B's is smaller than B. So we can use binary search to find the location where the number of A's start to be greater than or equal to A. And we can use binary search to find the maximum possible value of R, which is the location when the number of B's is the greatest possible location where the number of B's is still less than B. And we can look at an example here. So if we have the value of L equal to 4, and here if the index starts from 1, so this is 1, 2, 3, 4. So if L is here, then, and this is the first sample input where big A is equal to 4 and big B is equal to 2. So if we find the minimum location where the A's are greater than equal to A, then this is the location here, and this is R, the minimum value of R. And then we find the next location where the values of B is still less than or equal to 2. So this is this location, since here we have a B and here we have another B. So if our R moves here, then we would have two B's in this region if we start from a L value of 4. So this means that our maximum R is here. And so if we do max R minus min R plus 1, then this would give us the number. So this would give us the number of R's that would work given a particular L. And if we just loop through the entire string for each L, if we loop through it and perform the same operation of finding the minimum R and maximum R, we can find the number of R's given a particular L that would work for every possible L value. And after we do this, we can sum all the values up to find our answer. And now let's look at the code. So here's my code for problem C. Here's the prefix sum. So here I first calculated the prefix sum after I inputted the values, the A, B, and S. And here I didn't use capital letters, but it's the same thing. And then here I do binary search to find the minimum value. So here I didn't call it min R and max R. Instead I called it left and right, which is equal to the min R and max R I wrote just now. And here I used binary search. I did binary search on the sum to find the smallest value where the number of A's is greater than A. And here I did binary search again to find the maximum value where the number of b's is less than b. And after finding the values through binary search, I have left and right, which is equal to min_r and max_r. And I do answer plus equals the maximum of 0 and right minus left plus 1. And I do this because in some cases, there might not be a the right value might be smaller than left, and we don't want to add cases that don't don't actually work. So we need to check a maximum of 0 to ensure that these are all valid intervals. And afterwards, we can just print out the answer. For problem D, we have a number line and initially person 0 is standing at coordinate 0. Afterwards, persons 1, 2 until n will arrive in this order and they will stand on the number line. And each will stand at a coordinate of xi that is distinct for all people. So for each value, we want to find each time a person arrives, we want to find for person 0 until r, which is the current person. Then we want to find the minimum distance between each person and the person on their left or right. And we want to find the sum of this distance, and we want to minimize the distance between the person on their left and to their right. And for each person that enters the number line, we want to output this number D. To make the problem clear, let's first look at an example to see what the problem means. So here, this is sample input 1, where the numbers given are in this order: 5, 2, 7, 4, and more numbers. But we can just look at the first 4. So initially, person 0 is already on the number line at position 0. So afterwards, person 1 enters the number line, so we have 0 and 5. So what the problem means is that for each person here, for person 0, we want to find the nearest distance to another person. And in this case, it would be 5, since the only other person beside it is at position 5. And then for person 1, we also want to do the same. So the nearest person is at position 0, and the difference is 5. So this will give us 5 plus 5 equals 10. So our initial answer is 10. Then afterwards, person 2 also enters the number line, and it joins the position between 0 and 5. So now we do the same thing. For each step, we want to find the minimum location. So for person 1, the minimum location would be 2. So 2 plus person 2 is also 2. And for the person at location 5, this would be 3. So we would get 7. And afterwards, the third person enters the number line. So they go here, and we also need to do the same thing, which is to find the minimum distance. And in this case, it would be 2 plus 2 plus 2 plus 2 equals 8, because the nearest is 2, and the nearest between these are also 2. And now, after seeing what the problem means, let's look at how we can solve this problem. So we can't just calculate this each time, because this would take too long. But then if we update each time we update the answer from the previous answer, then this would be quicker because we realize that for each. So for each number, for example, when 2 enters the position, it only affects the answer for this number, this number, and this number. So which is the numbers on the left and on the right, and the current number that we're adding. So, and in the case when 7 is entering the number line, it only affects the number 5, and since there are no numbers here, then it only affects the number 5 and 7. So only the positions on the left or right will be affected. And we can look at this. So for from these first to the second person, then our answer is initially 10. So 10, and then if we subtract the answer, because it affects the answers for the persons on left and right. So if we subtract the answer for each of them, then we get 10 minus 5, and then we plus the answers for each of them back. So each of these three numbers, which is plus 2 plus 2 plus 3 equals 7. I know this seems redundant, but this is only because there are only three numbers here. And we can look at the next case where this affects these two numbers. So we would subtract. So 7 subtract 2 subtract 2. Sorry, I mean we will only subtract the answer for number 5 because 7 is the additional number we added. So this would mean 7 subtract 2, and then we add. I meant subtract 3 because, yeah, because 7 is the number we added. So this was the original number, which is 3. So 7 subtract 3, and then we add 2, which is the answer for 5 and 7. And from this, we get 8. And we do the same thing when we add the number 4. So we subtract the answer for 2 and 5, and then we plus the answer for number 4. So 8 minus 2 plus, and this is still 8. So what I mean from this example is that we can just subtract, since for each addition, it only affects the number on the left and right. So this is the number that's added. And then, so we can first subtract the original answer for the left and right value, and then we add back the new answer for all three of these values. So now let's look at the data structure that we can use. So we can use a set to store these values because a set automatically sorts the number in order, so we don't have to manually store it each time. Then we find that each number added only affects the answer of the two nearby numbers, which is the number only left and right. And then we keep track of the current answer. So we notice that on this example, for each step, we updated the answer from the previous one. So we keep track of the current answer. Then we subtract the old answers for the left and right values. Then we add the new answer for the left, right, and current number that we added as we did in the example. And to do this, we can use binary search to find the location of the number that it would be added. So we first don't add the number, then we use binary search to perform these calculations. And to do so, we can look directly at the code. So here's my code. I used a set to store the values, and then I inputted the values x in order. And I also inserted a very large negative value and a very large value into my set, because this way I don't have to check for boundary conditions. So I don't have to check if the current number I added is like in the boundary position, then that would be complicated. So I added a very small and very large number into my set. And this is the original number that's already there, which is the number at position 0. Then here's what I mentioned. I used binary search to find the position where my number would be added. Then I subtracted the number of the left value and the right value. Wait, this is actually the right value and then the left value, because I subtracted 1 from my iterator here. And then I inserted my current value. Then I did the same thing, which is to add back the left, right, and current value. So here I used binary search to find the position again. Then I added back the distance, and we can find the minimum distance between the left and right using this. So the absolute value of the left value compared to this current value, and the right value compared to this current value. So, and then this would give us the minimum distance between our current position and the right and left position. And we repeat this for all 3 positions. So the current position, the right position, and the left position, adding all of their answers back to our answer variable. And this gives us the answer for this current case. And we can print out the answer. Next, we look at problem E. For this problem, we have strings A and B of equal length that consist of the characters 0 and 1. And we can perform the following operation several times, which is to move the first character of A to the end. So this means that we can look at this example, we can shift the characters. So for this test case, if we perform the operation twice, the 1010001 would become the string shifted to the right 2 times. And this makes A equal to B. So we want to check whether some certain number of operations on A would make it equal to B. For this problem, if we compare all the possible shifts, then we can know whether some operation is possible. However, if we compare all possible shifts by finding the substring each time, then this would take O(n) time if we find the substring. However, so if we want to do this faster, we can use hash to do this check in constant time. And a hash is basically a method to convert a string into a value, and then we can compare the values quickly to check if the values are equal, then the strings are equal. And the hash can be calculated quickly because it can be calculated for the whole string, and then we can get the value for some certain substring quickly. So this allows us to check whether these strings are equal. And let's look at the code to see how this is implemented. So here's what I did. Here's my class for hash. And I first defined my hash string. Then I inputted the strings A and B. Here is I'm checking over all the possible shifts. So all the possible shifts. And if I want to check whether they're equal. So get hash is my function to return the hash for a specific range, of values from start to end. And this allows me to find the hash for, I can check my string in two ranges, which is the parts that's shifted to the end and the part that's not shifted. So the part that's um shifted to the end would be from 0 to j. So my j here represents that I did j operations on A. So I shifted the string 0 to j to the end. And this I will check whether it's equal to the j characters at the end of B, because I shifted the beginning of A to the end of A. So I will compare it to the end characters of B. Then here I will check the next part, which is the parts that's not shifted. So the location from j to a dot length. And my function is defined as like non-inclusive. So it's j to a dot length. And this I will compare to the beginning of B, because if I shifted the first characters of A to the end, then this part will be at the beginning. And I will compare it to the beginning. I will use get hash to get the hash value for this range, and I will compare whether these two are equal. So if they're equal, then this means that there is this operation which makes A equal to B, then we will output the value J. And the answer, I will set the answer to true. And otherwise, if the answer is false, then this means that there is no possible operation. Next, we look at problem F. For this problem, we have an integer n and a string s of length n minus 1 consisting of characters L and R. And we need to satisfy the condition that when the ith character of s is L, then the number I plus 1 is written to the left of I. And when the ith character of s is R, then the number I plus 1 is written to the right of I. So we're trying to write the integers from 1 to n in some order that satisfies these constraints. And we want to get the number of integers that can be written in each cell. So for example, here for the first test case, which is RLLR, then we have these possibilities. Then the value of CI means that the numbers 1 and 4 can be on the first position, so we will output the answer 2. And the numbers 1, 3, 4, 5 can exist on the second position, so 4, 1, 3, 5. They can all be on the second position, so the answer for the second position would be 4. So this is what we're trying to output. And for this problem, this is again the first input case. And if we're given RLLR, then this means that for the first number at position 1, then this R means that the number I plus 1 needs to be to the right of I. So 2 needs to be to the right of 1, and these LL means that 3 needs to be to the left of 2, and again 4 needs to be to the left of 3. So this is the order. And this one means that 5 needs to be to the right of 4. And this is all the possible combinations that we can have if we have these constraints. This does not mean that there can't be like some number in between. So it can be like 2, 2, 3, 5, 4. So it doesn't mean that 2, 3, 4 have to be continuous. Instead, there can be like some numbers in between. It just needs to be like the relative order between the numbers needs to be 3 is on the left of 2 and 4 is on the left of 3. And from this, we can find that the number 1 appears on location 1, 2, 3, 4. And it's like continuous because the number 4 appears on locations 1, 2. And the number 3 appears on location 2, 3, 4. And from this, we can find that the positions for each of the numbers is a like continuous range. And if we want to find the number of possible values that can be on each position, then what we can find the range. So for each number, we can find the range that it can appear on. So the earliest position that it can start to appear, and the latest position that it needs to appear. And if we get this range for each number, then we can use this to do. We can use like a prefix sum to calculate the number of values that can be on each position. So for this case, the earliest position for number 1, the earliest position would be 1, the latest position would be 2. For number 2, the earliest position would be 4, the latest position would be 5, because it can only appear on 4 and 5. And for number 3, the earliest position would be 2, and the latest position would be 4. And if we have the range for all of these numbers, then we can use a prefix sum to calculate the position, the values in each position. And so now, since we can do this, what I mean is in the prefix sum at position 1, we would just add 1. At position 2, we would subtract 1. And like this is what I mean. And this is how we can calculate the number of values in each position. So now we need to find the earliest and latest position where the numbers can appear. And so this is what I just mentioned, which is each number can appear in ranges. So we need to find the smallest and largest locations where each number can be in. So to do this, we can define 4 arrays called LL, LR, RL, and RR, because we find that the position only is based on how many values need to be like in front of the current value. So for example, um, for the number 3, we know that the number 4 needs to be in front of 3. So it cannot be the first value. So the earliest possible value that it can appear in is 2. And we also know that the number 2 needs to be to the right of 3. So this means that it can't be to the left, it can't be at the end, so it can only go up to position 4. So the the range is 2 to 4. And so this relates to these 4 arrays, which is LL, LR, RL, and RR, where LLI means that the number of continuous L's to the left of I. So the number of continuous L's to the left of the current position, and LRI is the number of continuous R's to the left of I. And RLI is the number of continuous L's to the right of I. So small will be defined as LRI plus RLI, and large will be defined as LLI plus RRI. And this is because LRI represents the number of continuous R's on the left of I. So for example, if we have I at this position, I, then LRI would be 2 because there's 2 continuous R's to the left, and RLI would be 3 because there's these 3 numbers, these 3 characters L here. And this is because this means that the number 2 is to the right of 1, and the number 3 is to the right of 2. And the L means that the number 4 is to the left of 3, and the number 5 is again to the left of 4. And so this means that all these numbers need to be to the left of 3. So meaning that the smallest position of 3 would be at position 5. And large is a similar case, except this means that these are the numbers till the end. So some numbers, some amount of numbers till the end of the array. So this is the largest value. The number needs to be here. And now we can look at the code. So here's my code for this problem. I defined my 4 arrays, and okay, wait, this is not needed because I used vectors. Oh, I used vectors. This is important because if I used arrays, then I need to redefine it every time, and that takes up time because I need to reinitialize it to make the values 0. So I used a vector. And here I calculated the values for LL, LR, these 4 arrays. Then here's the value for small and large that I mentioned. I did n subtracted by LL, RR because I need to subtract this value to get the actual position, because this value represents the number of values that will be to the right of our current value. So here's the prefix sum. I added 1 here to small, and I subtracted 1 to add the position of large. And if I sum these all up, I would get the answer that we want, which is the possible values at this current position. And we can output this answer. And thank you for listening to today's explanation.